So good afternoon to the second live session of the PCA course. If there are any questions, you can type in the chat box and we'll be happy to answer them. Okay, so until some questions come up, maybe we can spend the time looking at the topics which we've covered during the past few weeks after our first live session. So maybe I can share my screen and we can quickly go through some topics which were taught in, I think, week 4, 5, 6, and 7. Okay, so yeah. Oh, you let me stop sharing and reshare the presentation. Okay, so in the module 3, we started module 3 in this week and been continuing with the lectures on cache coherence protocols. So MSI was covered in the previous lecture, and in lecture 8, we start with the MESI protocol. So these were the 4 protocols which we are going to look at. VI and MSI were done in the previous weeks, and in the current weeks which you've covered from live session 1 to live session 2, we have covered the MESI and the Dragon protocol. Okay, so a quick recap about the MESI protocol. There is a 4-state protocol. Let's go to the FSM. So the states are, M stands for modified, E is for exclusive, S for shared, and I for invalid. Okay, let me go to the protocol FSM. Yeah. Right, so initially the block is invalid, and whenever there is a read or write request, we have to take actions accordingly. So if the current processor wants to do a read, so we get a signal processor read. So on the processor read, what should we do? If we are in the state I, we don't need to take any action. and we can move to the state S, or we can go to the state E. Okay, so when do we go to this or that state? That depends on whether there are other sharers in the system. So on a processor read, if we send a bus read signal and this wired odd signal S is true, so the true signal means there are other sharers and we have to go to a sharing state. Alternatively, if the S signal is negated, that is you have S bar being true, then there are no other sharers in the system and we go from I to E state. So on a processor read, we have these two options, and this is the condition used for the transition. While in state S, if there is a processor read, no action to be taken, we can simply read the block because we already have the block in a read-only state. Now, what happens on a processor write request? If we are in the state I, that is, we don't have the block, and a processor write request comes, we have to send a bus read X. Because it is an invalidation-based protocol, we have to inform others if the current processor is going to modify the block. So we send a bus read X, and that takes us to the state M. State M stands for modified. So once we reach the state M, then the block write can take place. All right, so if we are in state S and a write comes, then what should we do? We should again send a bus read X. Even if we have the block, we should send the bus read X signal on the bus, because this signal is going to inform the other sharers to invalidate their copies. So from S, we move to M, and when we are in state E, E is a special case or special state in the MESI protocol. It says the current processor has the block in exclusive mode, but it is exclusive read only. It doesn't have permission to write. It only says that the current processor is the only sharer of this block in the whole system. So when we are in state E and you get a processor write signal, we go to state M without any bus transaction. So we have a dash here, right? So no bus transaction takes place. And when in state M, we can perform reads and writes. So that is for the current processor. Now assume that this processor is the receiving processor and there is another processor in the system which is sending the bus reads and writes. So this bus read, which is in the blue arrow, was sent by the current processor. Suppose somebody else sends the bus read, then how do we handle it? So these are handled by the red color arcs. Okay, so if we are in state I and on the bus we see any of these signals, we have nothing to do because we don't have the cache block. But if our state is S, we are the shared state, and if you see a bus read, what should you do? It's a bus read. Somebody wants to read the block. Again, no action needs to be taken there. But if a bus read X comes, read exclusive meaning somebody wants to modify the cache block, then this processor has to invalidate its block. Hence, it has to go from state S to state I. While doing this, there is an output action called flush prime. So this flush prime says that if who should give the block to the new reader or the new writer. It depends on the implementation. If we permit cache-to-cache transfers, then one of these caches will give the block. If we don't permit cache-to-cache transfers, then we say that let the memory give the block. Okay, right. So this was when in state S, if you receive a read X signal, we move to state I. If you are in state E, if you receive a read X signal, this one, again move to state I. And if you receive a read signal, then we can move from E to S, because now there is another reader added to the system. So this processor cannot remain in E state. It has to go to the shared state. All right. Then state M. In state M, if you receive a bus read, then current processor has the most recently modified data. So it has to provide the data to the other processors. Hence, this flush is required. So on a bus read, flush the data block and then go to S. Remember that we are retaining the block. We're not invalidating it because we still want to use it, and the other request is only for reading. But if the other request is for write, that is bus read X, then we provide the block and go to the invalidation state. Okay, so this is the overview of the messy protocol. Right. So we've discussed this, who will give the data, cache-to-cache sharing. And there's complexity in cache-to-cache sharing because if there are multiple caches in the system, everybody has got the correct block, then who will give the block? Okay. Okay, so next we are going to quickly do a recap of the next lecture, which is on the Dragon protocol. Yes, so Dragon protocol is a write update protocol. And because it is a write update protocol, we do not have the bus regex type of messages, but we have a bus update message, bus UPD. This is the update message, which is used by the Dragon protocol. And here, the state S, which was there in messy, is divided into two different states. One is the SC and the other is SM. SC is for shared clean and SM is for shared modified. Okay, so shared clean state is similar to the state S in the messy protocol, where multiple caches share the block in a read-only manner. However, in messy, when the state is S, the block is updated or up to date in the main memory, whereas in Dragon protocol, the block may or may not be updated in the main memory. That is the difference between the SC and the S state. The next state, SM, which is another variant of the shared, is called the shared modified. So this state says that the current cache has the block in a modified state. So the current cache has modified the data block. But when the block was modified, the contents was broadcasted to the other sharers because we have the bus update protocol. So when we modify the data block, we update other caches with the most recent value. So the bus UPD transaction is going to broadcast the changes to the other sharers. However, the current cache has modified it, so it retains its state as SM for modified. As it's clear that the memory is not updated because the block is again going to be changed, and there is no point in changing the memory contents each time we do a write. So memory block will only be updated when we delete this block from the cache. We don't particularly use the invalid state here, but it is implicit in the protocol. And there is no point in changing them. So we'll go to the each time we FSM. So the Dragon finite state machine for the write update based protocol. Okay, so the state I is not shown here, but it is implicit in the diagram. So initially the block is not available, it's invalid state, and when we receive a read request from the processor, so let us look at the top left corner. When you receive a processor read miss, okay, a read request has come and the miss says that this is coming from the I state. Okay, so when this happens, we send a bus read signal and we'll either receive a bus with the shared signal S to be true or to be false. If the shared signal is false, that is there are no sharers, we can go to the state E. If the shared signal is true, look at the right hand side, then we go to the state S. Now here, because we are doing the read, we'll not go to the state SM, but we'll go to the state SC. Okay, sorry. So on a read, we either go to E or we go to SC. While in state E, reads can happen easily. While in state SC, even reads can happen easily. So we'll remain in these states until a write request comes or some action on the bus happens. Let us look at the bottom left corner when we receive a processor write request and the block is absent. So it is processor write miss. So we are coming from an invalid state. Here we'll send a bus read signal. We'll send a bus read signal and we'll wait for the shared wire dot signal S. So if S is true, meaning there are other sharers in the system, what should we do? We're performing a write. So the state changes to SM, and at the same time, the data which was changed has to be sent onto the bus so that others will update it, right? So that's why we've put two actions here in the bracket, bus read S semicolon bus update. So this update will take the data item to other sharers. The current state becomes SM. A similar action happens here when we have the S bar signal being true. So S bar says there are no other sharers in the system. So we move from state I to M, and we move from state I to M. Sorry, wait a minute. But we do not send a update. Why don't we update? Because there are no sharers in the system. S bar says that there are no sharers. All right. So these two actions we've looked at. Now what happens with the bus update that we are sending? We send this bus update when we perform the write, so there will be receivers for that. So the receivers are shown in the red color arrow. Here, let us look at the top right corner. So if another cache is in state SC and it receives a bus update, what does this tell? That the new data item is coming. Let us grab the data item, right? So the cache takes this data item, updates its copy, and still remains in SC because it was not the originator of this particular write. Okay. Now when in state SM, if a bus update comes, right? So we are in state SM, the current cache has modified the data item, but it receives a bus update. So what does this indicate? This indicates that there is another writer in the system who has changed the data item and has sent us the updated copy. So now we have to update our copy and relinquish the SM state. So on a bus update, look at this arrow. When you get the bus update, grab the data and move to state SC. We can't remain in SM because we are not the most recent writer to the block. All right. Now, so that's update. And if you just see a normal bus read, on a bus read in exclusive state, if you see a bus read, we should go to state SC because now we are not the exclusive single copy of the block, but there are other readers, and so we go to state SC on a bus read. While in state SM, if a bus read comes, what does this say? There is another reader into the system, and who's going to provide the data to this reader? Here, because our state is SM, we have modified the data block, so it's our responsibility to give the data block. So we have this flash signal here. Remember that in state E, we did not have the flash because here it was the fresh copy, and here the memory will give the data, whereas in state SM, the current cache has to give the data, so we have the flash action. The flash action is also associated with the state M because again in M we have modified the data block. So on a bus read, we have to flash the data item. But what is the next state? See, the current request is for read, so the other processor is a reader and not the writer. So we still retain the permission to have the state as SM because we have modified the data item most recently. So our state remains SM. Okay, so that's the Dragon protocol, which is a bus update based protocol, but it is still a write back protocol. Write back because the block will be updated in the main memory when the block is evicted. Now, who will evict the block? Suppose SC evicts the block. Okay, the cache having the state SC removes the block. So should it update the main memory? See, it was reading the block. It is holding a read-only copy, so it need not update the main memory. Similarly, when in state E, if the block is deleted from this cache, we don't need to update the main memory. But in state M, if the block is removed from this cache, the block is in dirty state. It has to be modified in the main memory. Similarly, if the block is in state SM, same actions, we have modified the data block. We are the most recent owner of this data block, hence we have to update the main memory. So when a cache in state SM removes the data block, it will update the main memory. Okay, so in this lecture, we've seen detailed descriptions of all these actions. And we also saw a detailed example of the state changes and then the proof that it satisfies coherence. Okay, so the other topics which we covered during these few weeks were coherence misses, and we've done a detailed analysis of uh, different types of coherence related misses, true sharing, false sharing, and so on. Then we looked at the internal implementation issues of coherence, that is split transaction bus, atomic bus, single level cache, then multi-level caches, and so on. So many interesting topics were covered during this week. So I guess you are studying them well and revising it, doing the assignments on time. If you have any doubts, you can post them in the mailing list. And best of luck with your studies. And I hope to see you again in the next live session in the next month. Thank you for joining in.